That's a lot of force. Okay? And what is Jimmy going to do?
Fly and maybe die.
He's going to slide right off his chair, right?
Yeah.
Okay? Because there's nothing there to get in the way. Well, let's say he only pushes with 300 newtons of force. Now we need to know, is there enough friction to overcome, or is there enough friction where Jimmy gets pushed off his chair? And the question is, how much friction is there? So if there's 300 newtons that way, then if there's 300 newtons this way, this is going to be force of friction, and this is going to be what we call force applied. If the force of friction is 300 newtons and his force applied is 300 newtons, does he move? No. What if his force of friction is 200 newtons and his force applied is 300 newtons? Does he move?
Yes.
Yes. He will accelerate with a net force of 100 newtons. I'll say that again. If his friction is 200 newtons and the force applied is 300 newtons, he would have a F net of 100 newtons. I'm sorry, I shouldn't be using this green on with the lights out. You guys still want the lights out, or do you want me to turn the lights on? You want them off? Okay. So
why is the arrow pointing that way?
because it's wrong. It should be pointing this way. Very good point. That's an excellent question too. We'll talk about that in just a little bit. Hold that question for the next minute. Okay? So does this idea make sense? Net force is an unbalanced force. If you have 800 up, 800 down, you have no net force in the vertical direction. But if you have 300 that way and 200 that way, you have a net force of 100 that way. Does the idea make sense?
Shouldn't it be equal though? I'm confused on how friction can be less than the force applied.
He overwhelmed the friction. He just overwhelmed its ability to produce friction. Exactly. Yeah. You just overwhelmed it. Like okay, next thing about friction. If I push on this cabinet, this is a very heavy cabinet. Let's say I'm pushing with 400 newtons. Do you see it not moving? So what's the friction pushing back? 400 newtons. What if I push with 500 newtons? Do you see it moving? It did?
Did you not hear it creak?
Well, it creaked, but it didn't move. Okay, so let's say it didn't move, because it didn't. I'm looking at it, didn't move. So I'm going to push with 500 newtons. What's the friction force? 500 newtons. What if I'm pushing with 600 newtons? What's the friction force? 600. You get the idea? So friction force, like normal force, can adjust to whatever it's opposing. Can friction force... Okay, does that make sense? Give me a thumbs up if that concept makes sense. Okay, and then the question. Can friction force ever be larger than applied force?
Yes. No. Yes.
Well, let's think this through.
Yes, you can.
If Torsten pushes with 300 newtons and Jimmy's butt applies 350 of friction, Torsten pushes that way. Which way does Jimmy go? Backwards. Does that make sense? No. Can friction force ever be larger than applied force? No, it cannot. So friction force has an upper limit, just like normal force. It will adjust to whatever it's resisting, but it can never be larger than what it's resisting. Friction force will never be larger than applied force, just like normal force will never be larger than applied force. Does that make sense? Okay, do you want to see some numbers? I know how much you love formulas. Okay, two types of friction before I give you the formulas. Two types of friction, static friction and kinetic friction. Static friction is the friction you have to overcome initially, and kinetic friction is the friction you have to keep overcoming. Okay? So static friction is the friction you have to overcome before an object moves. Kinetic friction is the friction you have to keep overcoming. So you want to move that dresser, you push on the dresser. First you have to overcome the static friction, then you have to keep overcoming the kinetic friction.
Your question kind of makes no sense.
The cat one or the?
The cat.
Well, it's a joke.
The rest of the video, the cat like jumps, but it's behind like slits and it falls to the cat.
Yep.
What's the joke?
Okay. All right. So first of all, static friction, kinetic friction. Do you understand the two concepts? Give me a thumbs up if you want. One thumb if you understand static friction. Two thumbs if you understand kinetic and static friction. All right. Which one is bigger and why?
Static is a momentum.
Because you have momentum.
Kinetic, because it already starts with static.
Okay. All right. So you first have to overcome static friction, then you keep overcoming kinetic friction. You've done this in your lives. If you've ever moved anything heavy, you know you have to push on it and first overcome static. Then you keep overcoming kinetic. Which one was always bigger? Static. The physicsy question is, why?
Because as soon as you get it moving and it has inertia, so it kind of helps you along.
Exactly. The word we're looking for, if you read ahead, is inertia. So static friction has a little component of inertia. Once you push, so when you're pushing on your dresser, you have to overcome its static friction, and which includes a little component of inertia. But once you get it moving, and you're moving it with a constant speed, inertia is now working for you. Inertia is for objects at rest tend to stay at rest until acted on by an outside force. Objects in motion tend to stay in motion until acted on by an outside force. Or I like to say, teenagers in bed tend to stay in bed until acted on by an outside parent. Or teenagers at a party will stay at a party until acted on by the police. That's inertia. So yeah, static friction is always bigger because you have to overcome the inertia. Okay, my joke. A white cat and a brown cat are walking on a roof and start to slip. Which cat slips off the roof first?
Is it a racist joke?
No, not that I'm aware of. Okay, so there's a formula for friction. That's the force of friction. Friction force is equal to a vector modifier mu, called the friction coefficient, multiplied by the normal force. So friction force equals a coefficient times the normal force. Yeah, it's a guy who's like, he's sliding down his driveway.
What's the answer to your joke?
I'm getting there. You'll probably figure it out yourself. So when you're comparing two materials against each other, they have a friction coefficient. Does anyone know what this letter is? Mu. Yeah, mu. It's the, yes, very good. It's mu. It's mu, which is why there's a joke about cats. So the bigger the mu, the more of the normal force becomes friction force. The bigger the mu, the more of the normal force becomes friction force. If you have a mu of 1, like rubber on dry concrete, then you could potentially turn all of your normal force into friction force. If you have a tiny mu, like glass on water or ice on steel, then or ice on water, then you'll have a very small amount of your normal force turning into friction force. So then my question is, a white cat and a brown cat are walking on the roof and start to slip. Which cat slips off the roof first?
The white cat.
Why?
Of them, because they're slipping. They just slip. It
It's
just says so.
snowing.
The answer is, whichever cat has the smallest mu.
I thought it was because it's snowing outside. That's why the white cat's white.
Whichever cat has the smallest mu is going to have the least friction. So if you have a lot of mu, you get the idea. Okay. Okay, questions? Shall we move on? Are we okay? Holding on. Holding on. Okay.
How come you think rubber on dry concrete is so, there's so much friction, how come you can still spin it?
Because you can still overwhelm that friction. Yeah, you can still apply so much applied force that friction force is just too large. Or it's just not large enough. Friction force is not large enough. Yeah. So yeah, your friction force is still limited by the materials. So if you have a really, really light car, okay, so when I was in college, guys up in Oregon, when it would get muddy, they'd put bags of cement over their back wheels in their truck because their trucks were rear-wheel drive because we were poor. We didn't have four-wheel drive, we had rear-wheel drive cars. And why would they put a bag of cement over the wheel wells on their back tires? Make them heavier. So when you increase the heaviness, you increase the what? By increasing first the normal force. So by increasing the weight on the wheels, they increase the normal force on the road, and then their normal force multiplied by the road coefficient given the friction. So they get more friction. Okay, other questions before we move on? Give me a thumbs up if you're ready to move on. Moving on. Okay, so Newton's first law is inertia. Again, like I said, for teenagers in bed tend to stay in bed until acted on by an outside parent and so on. So there you go. Object at rest. Again, if you need to write this down word for word, I'd be a little concerned about your aptitude in general science classes. So please write it in your own words. So an object rests or remain at rest until an outside force acts on it. An object will remain moving in a constant direction until outside force acted on it. So in summary, an object will remain at rest or maintain its state of motion until acted on by an outside force. Inertia is a property of mass. More massive objects have more inertia.
Simulation kind of makes it look like the ball is facing this and like the really small part of the wall.
Yes, this 30-year-old cartoon. So you've all experienced inertia. When you've been walking along and it's really dark and you kick the dining room table, and yeah, so that hurts because your foot wants to keep going forward, but the dining room table's in the way. So the bones in your foot keep moving forward and they squish the tendons and the muscles and the gunk in the front of the bones. Not fun. Inertia is also a big deal when we talk about collisions. Because what kills you in a collision, in an automotive collision, what kills you?
Crippling depression.
Yeah, it's not you traveling through the windshield. It's not even you hitting the bumper or hitting the steering wheel.
It's the instantaneous stop.
It's your brain smashing into your skull.
Exactly. It's your brain slamming into the front of your skull. Brains don't like to slam into the front of their skulls. So, no, I mean, if you could drive your car really fast and get projected out of your windshield, but as long as you land in like a giant meadow of pillows, you're going to be okay. It's not getting launched out of your vehicle, it's that brain slamming into the front of your skull. Yeah. And again, also for Newton's first going into second law, if you ever have a net force, you have to have an acceleration. And that's Newton's second law. F equals ma. Force equals mass times acceleration. If there is a net force, there must be an acceleration.
So then wouldn't it be semi-safer to not wear your seatbelt because your seatbelt's going to hold you back when you hit and your brain's going to smash against the front of your skull?
No. Wrong. Sad. No. Your seatbelt does two things which are very important. One, it keeps you attached to the car, ideally, but it also stretches. Most people don't realize in a cataclysmic accident, your seatbelt actually stretches. That weave, you seem like you pull on seatbelt, it's like it's not going to stretch, but that weave is designed to stretch. So the goal is for you to go ugh, instead of ugh, or conk. So it actually stretches. So no, seatbelts are really, really great. They can dramatically reduce the time that your brain slams into your front of your skull.
What does that say in Kinetic?
It says the acceleration of a body is proportional to the net force acted upon it and inversely proportional to its mass, or F equals ma. So no, you don't. If you want to know what physics people like to write in textbooks, it is, and I quote, the acceleration of a body is proportional to the force acted on upon it and inversely proportional to its mass, or F equals ma. Okay?
Just about what height is water like feeling become concrete? Like when you jump in?
Oh, it depends on how fast you hit it. So it depends on what you feel like hitting like concrete feels like, and how you hit it. So if you agitate the water, you'll be able to fall from a higher height, and it won't hurt as much. If you put soap, so if you're going to fall, if you're going to work really high over water, carry some Dawn dishwashing soap with you. And if you're like, oh, I'm falling to your death, squish a bunch of soap first. It'll break the surface tension, and you'll go right through the water. So if you're falling to your death, realize it is the cohesive forces of the water molecules that the particles can't get through. Like a bullet, it's going so fast, it has to push so many water molecules apart. All those water molecules have inertia. They don't want to get pushed apart. Well, if you're falling to your death, you get some Dawn dishwashing liquid and go squish, and the Dawn dishwashing liquid will be moving a little bit faster than you. It's going to hit the water, and it's going to break the surface tension of the first couple trillion molecules, so you'll survive more.
Yeah.
So there you go. So always, if you're working over water, carry some dish soap just in case. Get ready anytime. All right. So
shooting the water molecules.
No, because you're not going to be able to push the water molecules out fast enough. You'll make a little bit of agitation, but it's not really going to do much.
Just carry a grenade.
That might not be good either, because grenades, they take 5 seconds to go off. So in 5 seconds you're falling 250 meters, so you're going to fall a long way.
Yeah.
Or 125 meters. So you're going to have to throw it too. Okay, so what do we use Newton's second law for? We basically use Newton's second law to figure out what A is. A force divided by a mass is going to give us our A, and then we're going to plug in our A for V equals AT, and VI equals 1/2 AET squared. Okay, Anais, you got a question?
Oh, yes, I was going to say, if you had like, this is kind of a weird question, but if you...
Most of them are.
Yeah, okay. If you had like a machine that squirted Dawn dishwashing soap out in front of you, like this far in front of you, in front of your whole body, but while you're jumping, could you belly flop and it wouldn't hurt?
No, it would still hurt, just wouldn't hurt as much.
Okay.
So that's your lab this weekend. Get a couple like buckets of Dawn dishwashing, throw it into your pool, and then do belly flops and see what happens. All right. For those who like physicsy terms, Newton never wrote F equals ma. What he did write was the following, guys. What he did write was the following: the time rate change in velocity is equal to the time rate change in momentum. And that's something we're going to revisit when we talk about momentum. But basically what he's saying is the time rate change of velocity is the time rate change of momentum. Anyone in calculus in here, or had calculus last year? Okay, so a few of you know what time rate means. The derivative of change in velocity equals the derivative of change in momentum. We'll revisit this concept later. And then Newton's third law. Everyone loves Newton's third law. It's a good place to end. We'll pick this up tomorrow, but we're not done yet, so don't back up. Newton's third law says for every action, there is an opposite and equal criticism, or reaction. This is from a movie that was made the year you were born. It's called The Matrix. And in this scene, Trinity jumps up and she kicks this cop who easily has twice her mass. And the cop goes, wow, bam, into a brick wall. Here's the problem with that.
She doesn't go back.
Yeah, she didn't go anywhere, and she has a lot less mass. So if Trinity kicked the cop with 10,000 newtons, how many newtons are applied to her foot? 10,000 newtons. So Newton's third law creates what are called force pairs. Just like your butt is applying force down and your chair is applying force up, that's a force pair. Okay? So for every action there's an opposite and equal reaction, and this creates force pairs. I have this really nifty doodad set up with 2 force sensors, which we will use tomorrow because we don't have time to do it now, where we're going to find out what happens when 2 cars are connected to each other. What if one of them is accelerating? What if the other one's accelerating? So a force pair basically means 2 vectors in opposite directions at a point of contact. When you hit a ball with a bat, the force pair is the ball applies a force on the bat, and the bat applies a force on the ball. When Carson reaches around and slaps Woodbury because he's talking, hand applies force on cheek, cheek applies force on hand.
Do you think you would ever beat one of your students?
So it hurts.
On purpose? Oh yeah.
Blocking hands and fist apply force on hand.
Exactly.
That's why I like you were doing something from the flying.
So Elias fist on Chandler face, Chandler face on Elias fist, right?
That's
And
why.
Elias' fist is broken.
Yeah.
So like in videos where they do like the flying jump kicks and people like hit.
Yes. Yeah, they would have to slow down a lot. So what would happen here is if Cop Man flew back 30 feet or at 30 meters per second, Trinity would fly back at 60 meters per second because she has half the mass. Or more likely than not, she'd shatter every bone in her below her pelvis. It's the Matrix though, so physics doesn't apply. Anyone ever fired a shotgun like this? There's a reason shotguns have stocks. And when you saw them off and you put a handle on them, good luck, because they still kick.
What else is viscosity? How does that work?
What about viscosity?
Yes, like that's when water sticks and stuff, right?
Yes. Viscosity is a normal force that liquids apply to objects moving through them.
Is that friction still though?
Uh-huh. Yeah, we'll talk about that if and when we do fluids. Okay, so the takeaway from this before the bell rings is you cannot do a force without that force being done to you.
So you cannot. Okay. That is what he just said.